Today's video is going to look at the difference between displacement and distance. So very often these two get confused, and quite frankly, it's very understandable. Displacement is a vector, which means it deals with both magnitude and direction. So displacement is just a change in position. Again, position is a vector because vectors require knowing an actual location with respect to another point. And so displacement will just be the change between two locations, whereas distance is just literally measuring the length between two different points. So that would be a scalar value. You don't care if you're going north, south, east, or west. You don't care if you're going left or right, up or down. There is no direction necessary. It's just a straightforward length measurement. Displacement is a length as well, but of course we need to concern ourselves with where we started that length and where we ended that length. So as a brief friendly reminder, when it comes to scalars, we don't care about the actual direction. It's just all about the size, the length, or the strength of the measurement. So those are just examples there as a visual, whereas vectors actually involve arrows. So when I say arrows, I literally mean something that you see here. Eventually, we're going to get into two-dimensional vectors, and you're going to have to do some triangle diagrams. But otherwise, right here in the middle, you'll see a vector field, and that just shows between two charges, so a negative charge, positive charge, what happens with the electric fields as you move in this field diagram. Those are topics for a much different day, but it gives you an idea that vectors typically require arrows and therefore directions. So for instance, right here where the mouse is, the vector direction means the field is going upwards or to the north or away from whatever was right here. If I look at this vector diagram here, it looks like someone is walking or running or driving or flying, but they're moving from point A where the mouse is here. They moved here to the spot right there, and then they promptly moved to this point up there. If you look at the overall path that this person moved, you could just say they went from point A all the way up to the end of point B. So that would be an example of a displacement where it's looking at just where you started from and where you ended up. And so that's how vectors end up getting used. So when we deal with vector nomenclature, especially if it's just going to be one dimension, the previous example was 2 dimensions. When it comes to one dimension, very often we just like to use positive and negative numbers just to keep life simple. So I think in this video, I'm going to be using a lot of north, south, east, and west, but a lot of the times I'll just take that north, south, east, and west and apply positive and negative symbols with it. So usually if an object is moving to the right, we would call that positive. If you're thinking of a basic number line, if you move to the left, we would just call it negative. And likewise can be said for east and west. Likewise can be said for north and south. So north is typically associated with going up on your piece of paper, and south is associated with going down on your piece of paper. And so we just assign positive and negative based on your good old Cartesian plane. So your Cartesian plane, so typically everything's positive in this quadrant 1. Your x is negative in this quadrant 2, but your y is positive. Your x and y are both negative in this quadrant 3, and your x is positive and y is negative in this quadrant 4. So yeah, typically if we draw the north, south, east, and west, you can kind of see how that relates to x and y. But we're not going to work with 2 dimensions today. So this is the example I like to show in class very often. Usually your mind can work this out because a lot of times you guys would have probably driven in at some point in your life from Lloydminster to Calgary, and you know it's not a straight line drive. You don't just get to follow this red line. You can take this blue path up here, right? And it's according to Google Maps, it says if you take that blue path, it's 545 kilometers, and because you get to go 110 kilometers an hour, it should only take you just about 5 hours if you actually do that drive. If you take this grayish path, right, you're driving down secondary roads, and as you can see, there's a lot more zigzagging going around. It's a bit shorter of a distance, but it's still going to take you about the same amount of time as if you stick with that double lane highway, even though you're going about 40 kilometers further. So the distance, big one there, the distance is just literally measuring up all the little tiny lengths between each of these paths. All right, so this one's 545 kilometers, this one is 505 kilometers, and if you take this path south of Camrose, it's 506 kilometers. So these two are about the same distance, about, within a kilometer. So that would be the distance, looking at every little different path. The displacement doesn't care which path you take. The displacement is just looking at, okay, you started here, you ended here. It doesn't matter which route you took. That is what the displacement is going to look. And that's the displacement says you're only 370 kilometers from Calgary if you want to actually look at the straight line distance between Lloydminster and Calgary. So the only thing that can go that 370 kilometers would be a plane or a bird or something that can just fly over top of the road and not have to worry about zigzagging. So that would be your displacement. Displacement doesn't care about the actual path. It's just concerned about where you started from, where you end up in the end. So in that case, displacement is going to have to deal with direction. Now, this is a two-dimension problem, but kind of just like to use it as an example of what it means by where you started versus where you ended. It doesn't care what path you actually took. So as a little example here, I've got a person walks 10 meters to the east, then probably goes 20 meters to the west, and then finally moves 10 meters to the east again. So it says, draw a vector diagram. What is this person's distance displacement at each point of the trip? So when it wants you to draw a vector diagram, I'll get into more detail about this in class. Typically, you start with the starting point. I put two rulers over top of each other, so that way I can actually draw this all out on one sheet or one screen or one sheet of paper, if you want to think of it that way. So this green spot here, that's going to be my starting point. And so if I have to go 10 meters to the east, east is to the right. And so I'm going to draw an arrow that's 10 meters, right? Or in this case would have been 10 centimeters. So I would have used a scale. 1 centimeter is the equivalent of 1 meter. Right? It's always important to have a scale on there. Typically, I would draw this. That's a terrible arrow. I would draw this on my page 2 to indicate where north is. If you know where north is, typically east is to the right. So I often will do that. Just draw that somewhere on my piece of paper so it's obvious, and it's always a good idea to draw your scale as well. So this person is walking 10 meters to the east, so that means starting from this point here, I would draw a vector arrow. So vectors typically have arrows. I'll make the arrowhead bigger on this one to indicate where you've actually traveled. As far as what is the person's distance, well, the distance, they move 10 meters. Distance is just the overall length, so you'd write down D for distance is 10 meters. As far as what's the person's displacement, this is where it's different. So this is, the person is now 10 meters to the right of where they started at the 0 point right here. So I would say that the overall displacement is 10 meters east of the starting point. And so that's kind of the difference between what is a displacement versus what is a distance. So the numerical value, the magnitude, is the same for both of them right now. The biggest difference right now is displacement is involving the direction to the east. So we've passed this point. Then the person moves 20 meters to the west. So what that means now, oh, sorry, I'll keep it running total once in a while. So the person moves 20 meters to the west. So from this starting point, that person has now moved 20 meters to the left on the screen, because west would be left. So there's a vector arrow, a bit more obvious. All right, 10 all the way back to the 0 point here, and they've kept on going an extra 10 meters to the left. And so overall length of 20 meters. If I put that in terms of distance and displacement, from this starting point over here now, not the original starting point, but where the person left off, they have moved a distance of 20 meters. From this starting point again, this new starting point, the person has moved 20 meters to the west. And again, distance and displacement in this case will have the same magnitude. The biggest difference here is the west for the direction for our displacement. If I keep a running total of what's been going on, this point here in the green was our original starting point. So if I look at the total distance traveled, the person walked 10 meters to the right first and then 20 meters to the left. And so the total distance just keeps getting added up. So the total distance so far the person has traveled is 30 meters. We just add these two numbers together. You don't care the fact that one went east and then west, you would just ignore that direction. The person has traveled a total of 30 meters. Now, as far as the displacement is concerned, from this original starting point, this person is now located at a position 10 meters west of its original starting point. So therefore, its overall displacement is going to be 10 meters west. So now the 30 and the 10 no longer match up. So the magnitude is not the same anymore. Because again, we are trying to deal with direction here, and we're using this green marker as our overall starting point. So that's kind of the biggest difference at the moment between the distance versus the displacement. Every once in a while, your magnitudes will be the same, but then every once in a while, when you start considering going left and right, or up and down, you're going to end up having to involve some subtraction. But right now, I'm just going to keep a running total. All right, finally, person moves 10 meters to the east. And so what that looks like is now we have this new starting point. So we were right here, and we're moving 10 meters to the east. I'll make this arrow a bit bigger. 10 meters to the east would put us right back to our starting points. So again, if we just look at this leg of the journey, distance traveled 10 meters, displacement from this point right here is 10 meters to the east. If I consider the running total, well, we've gone 10 meters east, 20 meters west, 10 meters east. So if you add all of those together, you end up with 40. If we look at the overall displacement, we are back where we started. Right, we are back at our starting point. So therefore, our overall displacement is 0. Right? As far as we're concerned, it's if you turn your head and didn't notice a person move at all, and then you finally look back to the person, they're standing right back where they started. For all you know, they didn't move at all. So it is possible for your displacement to be 0. It's kind of like at the end of the day, you typically wind up back at home. So in the course of your days, you will typically have a displacement of 0. If you end up at grandma's house or somewhere else for the night, then your displacement is not 0 if you look at your overall daily travels. So in this case, our displacement is 0. So I don't bother with directions at this point because I don't really know where this point is. This is just a random point in the middle of the page. So if my overall displacement is 0, I just typically write 0. There's no need for meters typically. If your measurement is 0, the only real 0 measurements that require units would probably be temperature, because 0 degrees Celsius means something. But otherwise, if there's no overall displacement, you can't just write 0 without units, and as well direction. So what does that look like if you don't have to actually draw it out? So you have a couple of questions that are similar to what you see here. I think I have 2 or 3 coming up in this presentation. I'll try to do it nice and quick. So it says a man walks 35 meters east and then 185 meters west. So consider what your actual displacements are. I call them displacements because we're assuming there was a starting point, and he has 2 legs of this journey. So directions involved. So I'll call this displacement 1, 35 meters to the east. I'll call this guy displacement 2, 185 meters to the west. And if I look at the overall distance traveled, just like the previous page, I'm just going to add those 2 things together. So I'll take my 35 plus my 185, ignore what direction they're going, and just add them. So distance is pretty easy that way. You're always just adding numbers together. There's no subtractions. It's just positive numbers all the way through. We don't care where your final location is. We just add them together. As far as the man's overall displacement, we have to start considering, okay, 1 went east, 1 went west. So just like that vector diagram I drew, technically you have a subtraction. So you have to recognize, okay, well, what does that mean? You can't just add 2 numbers together if they have different units. So now we have to kind of see east and west as different units, no more than you can add $5 to 10 seconds. Right? You can't add $5 to 10 seconds. It doesn't make sense. So you can only add things when their units are identical. So east is not the same as west, but we have this little thing over here to kind of give you a clue of what to do. So east is a negative west. So technically, if I have a direction in the east, adding to a direction in the west, I can either change my east to a negative west and then just add properly. Or I could change my west to a negative east. So if I have the W symbol there in my square parentheses, I can just change that to a negative east. And it kind of looks like this. 185 is larger, so my west direction is probably going to be bigger. So I'm going to change this guy right here. I'm going to change my 35 meters east to a similar value, but in west. And so what that means is, since east is considered to be a negative west, I'm going to now change my 35 meters east to a negative 35 meters west. And now my units are the same. I have meters, I have the same direction, so I can actually add them together. So add these two together, it's just some quick little math, right? You'll end up with 150 meters to the west. Right? Don't forget the little underline there is just my way of indicating that as far as my significant figures are concerned, I have the precision to the one place, to the ones. And so I have to, since I ended up with a whole number, I have to indicate that this 0 actually is significant. Anyhow, so that's kind of how you do a question like this. I'll do a different example. A man walks 35 meters north, 129 meters south, 375 meters north, and finally 785 meters to the south. So in this case, we go same two questions. What is the distance and what is the displacement? So recognizing that we're now going north and south. So again, we're technically going up and down on the page if you want to think of it that way. So 35 meters north, its first displacement would be with the N. Second displacement has an S. Third displacement, N again. And fourth displacement has an S. So it's basically going back and forth in the up and down direction. So I guess up and down, up and down. The distance traveled, you literally just add them all together, right? Once again, you ignore any north or south as far as calculating displacement. So you just add all four of those together and then boom, you're done. You don't have to think about it any further. The displacement requires a bit of thinking. So, I better touch back on this. Yes, we now have four significant figures because according to all of these numbers, we have precision to the ones placement. So therefore, we just keep that precision. And in this case, for our adding, we can get a much larger significant figure count when you're adding numbers together. So just as a little throwback to significant figures. So part B, what is the displacement of the man? The displacement of the man is going to have to consider your north and south as a positive or a negative value. So if I write them all out, my overall displacement, I would just add all these together. And the man's going north, then south, then north, then south. And just like the previous question, we have to recognize that we can make them positive and negative numbers. So north is a negative south. So I can either replace this N with a negative S, or I can go the other way and replace an S with a negative N, but don't do both, right? And so in this case, I usually look at my numbers and go, okay, I typically prefer positive numbers in the end. And when you're dealing with north and south or east or west, you should just have positive answers in the end. If you end up with a negative answer, just change your direction. So if you end up with -5 meters west as a final answer, I'll just write this in. Don't leave it as -5 meters west, actually transform it into a 5 meters in the east. So when in doubt, leave it as a positive answer. So that's just a little bit of an aside. Back to this question. I look at these and I see my number 875 is pretty big, a lot bigger than even if we just added all these together. So I'm going to actually make south my positive number. Therefore, north is going to be negative. So anytime I see a north, I'm going to call it negative south. Then moving forward with that, since north is going to be a negative south, that changes my 35 meters north to a negative 35 meters south. It's going to change my 375 meters north to a negative 375 meters south. And then I can just add these positive and negative numbers together. And if I do that, I should get 594 meters to the south. If you went the other way and made my south values a negative north, that's fine. You just would have had an answer of negative 594 meters to the north, which is acceptable, but do try to make sure your answers are positive in the end. Right? It's kind of like it's less effort to have a positive number written down than it is to have a negative number written down. So change your direction accordingly. The last question kind of ties back to the previous lesson with the average speed. I think there's a couple on your homework assignment that will have questions like this. So it says, once again, a man walks 75 meters to the west and then 192 meters to the east. If it took the man 90 seconds, then what was the average speed of the man and what was the displacement of the man? So this one is thrown back to average speed. So recognize what we have. We have two displacements. One's west, one's east, and then of course a time of 90 seconds. So if you remember from before, your average speed is just your total distance divided by your total time. So this is deal with distance. So speed is just like distance. It does not care what direction you're going. And so therefore you have to find your total distance before you can move forward with the speed. So if I find my total distance, again, total distance divided by your total time, and there's only one time given, so that one's pretty straightforward. But your total distance is going to have to add both of these together without their actual directions. So then if I get rid of those vector arrows there, oh, I forgot the delta symbols. Oh well. So if I just add those two together, I'll get 267. Right? Divided by 90, that part's just math. I'll give you somewhere around 2.96 repeating meters per second. Once again, units are important. A meter does not get canceled by a second, so it remains as a meter per second. Please continue that forward. And then we look at what we actually have. We have, according to this, is 2 significant figures, and our result here is 3 significant figures. So we should just have 2 significant figures in the end. And so therefore, our final answer is going to be rounded up to 3.0 meters per second. So that is our average speed. So the question then says, well, what was the displacement of the man? So displacement of the man is once again going to have to involve a west and east direction. And so therefore we put them together. We're considering our directions. And as a friendly reminder, east is a negative west and west is a negative east. So in this case, I'm going to maybe change my west to an east because 75 is smaller than 192. So I end up with negative 75 east plus a positive 192, and its overall, the man's overall displacement is going to be 117 meters to the east. The next leg of this would be, well, what's the man's velocity? But we haven't gotten through velocity yet, so that's going to come up in another lesson or two. But if you can get all that, then you should be fine to do page 15. Page 14 was the previous assignment, but if you're a little behind on that, start on page 15 in your workbook. If you have any questions, just fire me an email and I'll get back to you as soon as I can.